All right, so let's go ahead and draw a bowling ball. And let's say that the bowling ball's mass is 3 kilograms. The speed is 6 meters per second. And we want to find out what the kinetic energy is of this object. So, we're very familiar with that. 1/2 mv squared, take the mass times the speed squared. Excuse me. We get 54 joules. And that is the translational energy, right? So the energy going left to right of this object. Now, it's also rolling though, right? So if you think about it, this object is rolling the whole time. And that's kinetic energy as well. That's energy of motion. So we want to figure out, what's going on with that. So inertia is how hard it is to stop or turn a moving object. And so if we look at this object, we have a 3 kilogram mass. It's has a certain radius. There's a couple factors that we look at. And we deal with moment of inertia with that. So it's how hard it is to get an object to rotate or stop rotating. And it's based on two main factors, mass and radius. So the greater amount of mass that you have, if you have an object, let's say, on a frictionless surface here, and you start to spin it, and you get it faster and faster and faster and faster and faster, the more mass that it has, the harder it is to stop or get it moving. And then also, if the radius is larger or smaller, it'll affect it. And so if you look at this picture, right, if you have this thing rolling at a certain rate and this one rolling at a certain rate, this is much easier to stop because even though it's about the same size, this has much less mass, right? And so in general, these are our two principles here. The greater the radius, the harder it is to turn or stop turning. The more mass you have, the harder it is to turn or stop turning. And yeah, and that's directly integrated within moment of inertia. So to recap, when we're talking about energy, we have the moment of inertia instead of mass. So kinetic energy rotational, EK is fine. It's the IB notation. 1/2 I instead of V and then omega squared. So translational is 1/2 mv squared, which is linear. Mass is, that. In this case, we're looking at moment of inertia, which includes looking at mass and the radius, and then the angular speed instead of linear speed. And so this is the energy of the rotation. This is the energy translationally. And if we look at different objects, for instance, one point object, we're just looking at the mass itself and then the radius squared for the middle. For two objects, we have 2mr squared. We have this mass and this mass, and we look at the radius and the mass, and that's the moment of inertia there. For a ring, we look at the entire mass, capital M, the entire mass of the ring times radius squared. And again, the more mass you have, the more moment of inertia. The greater the radius, the more moment of inertia. So if you have a ring that's like on someone's finger versus like an industrial size ring, obviously the industrial size ring's got more mass, more radius. It's got a higher moment of inertia. And then we have the other objects, right? And so, but all of them are dealing with how much mass do you have, and then also what's the dimensions like, length, radius, and the bigger the radius or the bit longer the length for the rod, the more moment of inertia that you have. And so again, it depends on both the mass and how close it is to the rotation. And so let's go ahead then for this and calculate the rotational kinetic energy. Let's say that the mass or the radius is 0.16 meters and it's going 6 meters per second, which we need to relate to what's going on rotationally. And yeah, I'll go ahead and calculate the rotational kinetic energy of this bowling ball. So go ahead and pause the clip and do that. And when you're ready to check, you can hit play to continue. All right, so the moment of inertia for a sphere is 2/5 mr squared. And we can get from our rotational or from our linear speed rotational speed, which should be 37.5 radians per second, and we should get an energy rotational energy of 21.6. So that is just the energy of the rotation itself. This is the translational, the linear, translational linear, the same word, same relationship there. So we can add those together, and we get to send, get a total amount of 75.6 joules. That's a total amount of energy that we're dealing with. And both looking at translationally, because if this was a flat surface with no rotation and was just moving along, that's the energy it would have. But it's rotating, and we've ignored that up to this point. Okay, so let's consider some of these objects here. We've got some disks that can have some energy we can look at. Let's say we have a ring that has a mass of 0.45 kilograms, radius is 0.2 meters, and it rotates with an angular velocity of 5.2 radians per second. We want to calculate the rotational kinetic energy of the ring. So the first thing we can do is draw it out, and we have a ring, we have a radius there, we have our mass, we have the angular speed, and we will find the kinetic energy. So I'm going to have you go ahead and try this, and so go ahead and pause the clip, and when you're ready to check your work, you can hit play to continue, but go ahead and try this one on your own. All right, so let's see how you did. We know the moment of inertia for a ring is the mass times the radius squared, and so we've got the moment of inertia there, 0.018 kilograms per meter squared. And then calculating the kinetic energy, 0.2434 joules is the amount of energy this rotating ring would have. Okay, so let's consider this object that's rotating, this disk that's rotating around a fixed point in the middle. If you notice, the closer you are to the middle, the shorter the linear speed. So if you consider, let's say, this spot right here, the linear speed, the tangential speed here is only this much, because as it rotates around the circle, it's going just around the middle part. I'll be right with you. And on the outside, it's covering greater distance, and so it's a faster, tangential speed the further you go out, because it's traveling this entire way around. So we're going to consider that here as we move forward. So if we have a tire that is, or a wheel that is slipping across the ground, in other words, it's not rotating, it's just sliding across the ground, every point along the tire has the same velocity. You can look at the bottom here, it's going this, like this, the top, each part is going, because it's slipping across the ground, it's not rolling. And so, each part has the same translational velocity. But if you have a tire that's rotating at the same time it's slipping, you have something, well, it's not slipping, but it's actually rotating. We get this situation, and this may look a little bit strange here. So if you think about it, the tire is rotating around, right? And as the tire rotates around, it has a rotational speed, but it's also moving forward. So what happens with this is the tire is rotating, and you have tangential speed from that, but then it's also moving forward. So it's a combination of those two. If you think about the bottom, the whole tire is going to the right, and so you have that velocity, but the rotational velocity is this way. So the combination of those two end up being 0. So to be able to visualize that, you have A here with the rotational velocities, and then B with the translational, and then again the combination of this and this make it 0 at the bottom. Combination of this and this make it a great amount at the top there, and then in between you've got the varying amounts. So again, the combination here for a rotating non-sliding wheel is the combination between those two, and then again at the top it's moving very quickly. At the bottom, the combination of the two make it 0. And so when we add this to the top, the total velocity is the angular plus the translational, again at the top, and then at the bottom we add up those two and they add up to be 0. All right, so now we can explore this a little bit more. We have a bike wheel that's rotating with a constant motion down the road. Diameter of wheel is 46 centimeters, and the bike covers 18 meters in 3 seconds. So we want to find out what's the fastest and what's the slowest total velocity in the bike tire. So we can fully work through that now. So let's go ahead and draw the bike tire, and we'll identify our variables here. We know at the very bottom, again, it's going to be 0. At the very top, we're going to have a combination of the rotational and the translational motion there. So why don't you go ahead and try this, and once you're ready to check, you can hit play to continue. So go ahead and pause, and then when you're ready to check, you can hit play. So we know the difference between the linear velocity and the angular velocity, we can get simply by multiplying the radius times the angular velocity. And so in this case here, 0.23 is the radius, and we know it's covering 18 meters in 3 seconds. So the bike is going translationally, it's going 6 meters per second. And so we're placing that in there. We know that velocity there is 6 meters per second, and the angular velocity therefore is 26.09 radians per second. So the combination of those two, right, the linear and then the angular, therefore will be a combination for a total of 6 meters per second at the very top. And so the second part of this that I had him do is look at the total only 10 meters or 10 centimeters away. And so when we do that, we can also find that. So go ahead and figure out what the total velocity is at the 10 centimeters away from the top there. And when you're ready to check, you can hit play to continue. So go ahead and pause and then give that a try. All right, so we know the angular speed here, or angular velocity, is 26.09 radians per second. So we can find the linear speed, which is 2.609 meters per second, and we add the two at the top there, so we get a total of 5.12 meters per second. The translational motion along the center of mass works just like we have something with a ball or anything else that we have going. And so let's say that we have a disc that's launched into the air with an initial velocity of 16 meters per second, an angle of 40 degrees of the horizontal. We want to figure out how far the disc will travel, and then also the rotational displacement if it is spun with a speed of 7.882 radians per second. So let's go ahead and draw the projectile motion here. We have the disc that's going through the air, an angle of 40 degrees. Figuring out how far the disc will go is similar to what what we've seen in the past, and so it's actually worked out the exact same way. So forget about it that it's a disk right now. Just pretend it's it's a normal projectile. We want to figure out delta x. How far does it go? So this will be good review. Go ahead and do that first, and then we'll start to unpack part B and try to figure out what's going on there. So go ahead and pause the clip and set this up and make sure you're in degrees when you do this to break up the x and y velocities. And then when you're ready to check, you can hit play to continue. Okay, so when we break up our x and y velocities, we'll be able to figure out our x problem or y problem, what we need. So we have our, for the x, right, delta x equals v initial times time. That's the only equation that works in the x direction. And so the velocity next, 12.26 meters per second, we're dealing with there, and the y, 10.3 meters per second for the velocity. And so we know that vy is 0 at the top. We can find the time halfway. The time halfway is 1.05 seconds. And so the full way would be 2.1 seconds. And when we place this in here, we get a velocity or a displacement of 25.73 meters is the displacement of the disk as it goes. So now the challenge is to know, what is the rotational displacement? What is, delta theta, right? What is the rotational displacement? So I'm gonna see if you can figure that out with your constant acceleration equations that we use for rotation. Do your best with that. See if you can determine the total amount of rotational displacement, and that'll be good. So go ahead and hit pause and give this a shot, and then when you're ready to check, you can hit play to continue. Okay, so the biggest thing here is we know that how much time is going by, 2.1 seconds. And we know that the speed is 7.82 radians per second. So in this case, there's no acceleration. It's staying the same. So we figure out, how many radians it covers during that time. So in other words, this disk, as it flies through the air, it's spinning, right? So it's spinning, 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 and then it hits. Question is, how many radians did it cover? 16.4, right? So again, if this is one radian, 1, 2, 3, 4, 5, 6, and a little bit more, and then it'll go around again, and then about a half after that.